Hi everyone. Today let's talk about section 3.5, derivatives as rate of change. So today we're going to talk about applications of derivatives. Big idea. The rates of change of many mathematical models are derivatives of functions of the quantity with respect to time. Big skills. You should be able to write a function that describes the quantity with respect to time, then find its rate of change by taking the derivative of the function. So the first model, one-dimensional motion. Suppose an object moves along a straight line according to an equation of motion. So S is the displacement, S equals f of t. Okay, so displacement is also the directed distance. It's also called position functions. So, distance is just magnitude, is positive numbers, right? But directed distance, it could be negative number. So negative number means it's opposite to the direction that you define to be positive. Okay, so you pick one direction and define it to be positive, and if the object travel, the position is toward that direction, then the distance is positive. Otherwise, if it's in the opposite direction, then the position function is negative. Okay? And in the time interval from t equals a to t equals h, the change in the position is f of a plus h minus f of a. Then the average velocity over this time interval a to a plus h equals, so we have like the secant line, right? We have change of the distance, change of the displacement over change of time. Okay, and you can see from this picture, the average velocity, it corresponds to this piece, right? This is the secant line. It corresponds to the slope of this secant line, where the instantaneous velocity corresponds to the slope of the tangent line. Okay? Yeah, so this is the instantaneous velocity, and we use v to denote. So v of a equals f prime of a. That is the limit of the change of f over change of t, right? So we have two expressions. Do you remember? It depends on how you call the second point. So the first point is always a. The second point, if you call it a plus h, then you're using this expression. If you call the second point to be x, then you're using the second expression. Okay, and remember, I suggest you to use this expression because it is consistent with when we take the derivative of a function. So you're gonna have x instead of a here. Okay, all right. So what is speed? Speed is the magnitude of the velocity, okay, which is the absolute value of the velocity. And acceleration is the derivative of the velocity, so that is the second derivative of the displacement. So I hope you have seen this terminology before in your physics class. Alright, let's look at example 1. Suppose a stone is thrown vertically outward with an initial velocity of 64 feet per second from a bridge of 96 feet above a river. By Newton's law of motion, the position of the stone measured as the height above the ground after t seconds equals this, where s equals to 0 is the level of the river. So let's draw some picture. So here we have a bridge, right? And then we have some river here. You're standing on the bridge and you throw a stone vertical outward. Wonder what happened with the stone. It will go back and hit the water, right? So the initial velocity, if we set the upward is the positive direction, then the initial velocity v of 0 is 64 feet per second because it's throwing up, so that's why the initial velocity is positive. And s of 0 is 96 feet, right? Because this bridge is 96 feet above the river. Okay, and we're given the displacement function. Find the velocity and acceleration functions. So part A, what is velocity? velocity is the derivative of displacement, right? So minus 16 stay here. Derivative of t squared is 2t. And 64t derivative is just 64. So this is our velocity. And when we multiply by negative 16 and 2, we get negative 32t plus 64. So this is the velocity. Oh, sorry. And how about acceleration? So acceleration is the derivative of the velocity. Well, the derivative of that is just negative 32. Well, you see, this is a negative number. This is actually the gravity, okay? So this is the acceleration due to gravity. So it's negative because the attraction from the Earth is pointing down, and so that's the negative direction. And we know the acceleration due to gravity, if we're living on the Earth, that is 9.8 meter per second square. Is also 32.2. But sometimes, in order to calculate and get a nice number, we just use 32, and this is feet per second square. It really depends on which unit system you're using. Okay, so this is the velocity and acceleration. Part B. What's the highest point above the river reached by the stone? Well, what happened when you throw the stone? What happened when the stone at the highest point? What is special about it? The velocity is 0, right? So at highest point, the velocity is 0. So let's find the time where the velocity equals to 0. Okay, so let's find the t such that the velocity is 0. So that's negative 32t plus 64 is 0. Let's add 32t on both sides. And we get this. Wow, let's divide it by 32. We get t equals 2 seconds. So what is the highest point? Well, then it's asking the what? Displacement, right? So we plug 2 into our s. We get minus 16, 2 squared, 4, plus 64 times 2, plus 96. Well, 16 times 4 is 64. So this is the same as 64 plus 96, which is 160. So far, so good. So the highest point is 160 feet. Okay. So for my class, if you forgot to write the units, that's fine, but it's only for my class, okay? So in your physics class, chemistry class, or your major class, if your instructor require you to write down the units, please write down the units. Just for my class, if you forgot to write the units, that's fine, okay? But in your other class, if you forget to write a unit, don't say that, oh, Suki tells me to. Don't say that, okay? So only for my class is okay. So part C. With what velocity will the stone strike the river? Okay, so strike the river, what happened? It struck the river, then what happened to what is special about it? The displacement is 0. So we want to find the time such that the displacement is 0. Well, the displacement is minus 16t squared plus 64t plus 96 equals 0. Can you see the common factor 16? Let's divide it by negative 16. I can also make the leading coefficient positive. Then I have 4t. Well, this is 6. Are we able to factor it? Not quite, right? The factors of 6 are 1 and 6, 2 and 3, but they won't give me 4 in the middle term. So let's use quadratic formula. Do you remember quadratic formula? 2a, so a is 1, so 2a, and then negative b which is 4, plus or minus b squared, minus 4ac. So minus 4ac, but c is negative, become positive. So 4 times 6, 24, 24 plus 16, 40. What's 40? 40 is 4 times 10. Square root of 4 is 2. Okay. Yes. So we can divide it by 2. Then it's 2 plus or minus square root of 10. And because we're talking about real life problem, your time cannot be negative. So you only pick the positive one. Right? How do I know the negative one is negative? Oh, think about it. 2. 2 is like square root of 4. Is square root of 4 bigger or square root of 10 is bigger? Square root of 10 is bigger. So 2 minus square root of 10 must be a negative number. So we only pick the positive number here. So we're looking for what velocity will the stone strike the river. So we plug this time into our velocity function. So negative 32t, t is 2 plus square root of 10 plus 64. Well, if you distribute it, you can see, well, the first term give you negative 64, and then second term give you negative 32 square root of 10 plus 64. 64 and 64 cancel. So we get negative 32 square root of 10 is our answer. And what's the units? Feet per second for velocity. So far, so good, everybody? Okay. Let's continue on example 2. Alright, we're given the functions. We want to describe the position of a particle moving in the direction of the positive x-axis, where s is measured in feet and t measures in minutes. Part A, find the velocity and acceleration functions of the objects. So here, velocity is the derivative of the displacements, right? So we take the derivative of the displacement, constant multiple stay here. 3t squared is the derivative of t cubed, right? 8 stay here. We have 2t, and then 9. Derivative of 7 is 0. Okay, let's simplify it. 3 and 6 cancel. We have 5 over 2t squared minus 16t plus 9. So far, so good, everybody? Alright, so how about acceleration? Well, we take the derivative of the velocity. Well, constant multiple stay here. We have 2t and minus 16, right? 2 cancel. We have 5t minus 16. Okay, so this is our velocity and acceleration function. So part B, we want to find the velocity at time equals 4 minutes. So what do we do? I strongly recommend for each of the example, please stop and try the problem first. And then after you're done, you can check your answers, okay? So we want to put 4 into our velocity function. So 5 over 2, 4 squared, 16, minus 16 times 4 plus 9. Okay, 2 and 16, we get 8. 5 times 8 is 40, minus 4 times 16 is 64, plus 9. Well, that is negative 24 plus 9, negative 15. Right, everybody? So negative 15 feet per second. Is the object moving to the right or moving to the left? Well, because you set the positive x direction is the positive direction, right? Then because it's negative, then it's moving to the left. Okay. So part C, acceleration. Acceleration, we want to plug in 4. Then 5 times 4 minus 16. Oh, that's 20 minus 16, which is 4. Okay, so 4 Is the object speeding up or slowing down? With some of you, will you say up because it's positive, so it's speeding up? No. When we talk about speeding up or slowing down, we want to see whether the acceleration is in the same direction as the velocity or is in the opposite direction compared to the velocity. You can see because this is positive, this is negative, so A and B are opposite direction. If it's opposite direction, is this speeding up or slowing down? Actually, it's slowing down. So be careful with that. Okay, everybody? Alright, so that is one-dimensional motion. So next mathematical model we want to talk about is growth models. Let P equals f of t be the population of a species or the consumer price index, where t represents the time. Then the average growth rates of P on the interval from A to A plus H. So average growth rates, change of P over change of time. So very similar, okay? This corresponds to the secant line slope. And the instantaneous growth rates is going to be the derivative, okay? So this is the slope of the tangent line. Alright, so let's look at example 3. The number of worldwide internet users, should be users. Oops. So internet users between 1995 and 2010 can be described using a function. So this is the function where t measures years after 1995. Part A. Find the average growth rate of internet users. From 2000 to 2005. So 2000 corresponds to t equals 5. Because 1995 it corresponds to t equals 0. Right? So we don't plug in t is 2000 there. It'll make the number super big. Okay? So part B, what was the instantaneous growth rate of the internet users in 2006? Part C, assuming that the growth function can be extended beyond 2010, what is the predicted number of internet users in 2015? Okay. Alright, so let's see. Part A, average growth rates. That is change of P over change of T. And so we're looking at 10 and 5. So P of 10 minus P of 5 over 10 minus 5. What is P of 10? Well, that means whenever you see T in the expression, we place T by 10. So T, so 3 times 10 squared, 100. Plus 17.8 times 10 minus 45.8. Subtracts. When you plug in 5, I strongly recommend you to put a parentheses here. Okay, and the bottom, 10 minus 5 is 5. Okay, so we plug in 5. 5 squared is 25. So this times 5 and minus 45.8. Oops, I almost ran out of space. So what is that? Well, that's 300 plus 708 minus 45.8. We want to get rid of the parentheses. And also we want to multiply by 3 and 25. That is 75. And minus become minus. 5 times 70.5. 5 times 8 is 40. 5 times 7, 35. 35 and 4 here, right? And also next, minus become positive. 45.8 over 5. Let's see. We can cancel this guy and this guy. And for the rest, let's plug into our calculator. Okay. So I get my answer is 115.8. Do you have the same answer? Okay, so that is the average growth rate from 2000 to 2005. So part B, what is the instantaneous growth rate? So what are we looking for? We're looking for the instantaneous growth rates. That's P prime of T. That's the derivative, right? Well, that is 3, and then derivative of T squared is 2T plus 70.8, right? And the derivative constant is 0. So this is 6T plus 70.8. And we're looking for the instantaneous growth rates in the year 2006. So 2006 corresponds to T equals what? 11, right? So P prime, we plug in 11. So it's 66 plus 70.8 equals 136.8. So far, so good, everybody. And part C, what is the predicted number of internet users in 2015? So 2015 corresponds to T equals what? 15? 20. So we put 20 into our population. So we have 3 times 20 squared plus 70.8 times 20 minus 45.8. So what do we get here? I put this in my calculator and I got 2570.2. Okay, so do you have the same answer, everybody? Yes? Alright, so this is our example 3 about growth rates. Next, let's continue. So we have cost. This is our last model, okay? Cost. In business and economics, the cost function gives the cost to produce the first X items in the manufacturing process. The average cost to produce X items is, so you use the cost divided by the number of items, right? So C of X divided by X. This is the average cost. What is the marginal cost? Marginal cost is the derivative C prime of T. So it's the approximate cost to produce one additional items after producing X items. Okay, so that is the derivative. What's the difference between average cost and marginal cost? Let's say if we are a factory, right? We make burgers, okay? So we make burgers. Well then, before you make the burgers, you need to rent a factory, right? You need to pay the salaries of the people and maybe electricity, gas and waters, okay? And plus the cost of each burger, right? You're gonna buy some meat and bread for each burger. So, but the average cost is you add up all the costs and then you divide it by the number of burgers you produce, right? But the marginal cost, you only count like the for producing one more burger. What are those costs? It is okay. But think about it. Even though you don't produce any burgers, you still need to pay the rent of the factory, right? So those are the fixed cost. And those costs will be average on the number of burgers you produce. But if you are talking about the marginal cost, and those costs won't be included. Okay, the marginal cost is the cost you produce one additional burgers after producing X burgers. Okay. All right. Example 4. Suppose the cost of producing X items is given by this. Part A. Determine the average and marginal cost functions. So the average cost is c of x over x. So minus 0.02 x squared plus 50x plus 100 divided by x. You can leave it like that, or you can simplify. So 50, x and x cancel, and then 100 over x. We can simplify like this. This is the average cost. How about the marginal cost? Well, that's the derivative of the cost function. So that's minus 0.02, constant multiple, right? Times 2x plus derivative of 50x is just 50. So we have minus 0.04x plus 50. Part B, find the average and marginal cost when x equals 900. So average cost, we plug in x is 900, so c of 900 over 900. Well, that's minus 0.02 times 900 plus 50 plus 100 over 900. Okay, let's plug this in our calculator, and what do we get? I get 32.11111, so the 1 is repeated. Do you have the same answer? And for marginal cost, so I got c prime of 900. I got minus 0.04 times 900 plus 50. Okay, so you know this 20 and this 20 cancel. 4 times 9, 36. 50 minus 36 is 14. So far, so good. So the average cost is usually bigger than the marginal cost, because the average cost takes into account of like the rent of the factory, electricity, and the salary of the people, right? Okay, that is our cost model. Now let's do more exercise. Okay. So example 5, the position in meters of a marble rolling up a long incline is given by this, where S is measured in seconds. So T is measured in seconds, and S is the starting point. Okay, S is 0 is the starting point. So part A, we want to find the velocity function for the marble. Okay, velocity is the, oops, look what I write. So velocity is the derivative of the displacement. Well, but the derivative, this guy is quotient, so we need quotient rule, right? So what's quotient rule? Bottom guy square, and then the top guy prime times bottom guy minus top guy times bottom guy prime. See? We just write down the quotient rule. And in the second step, we find the derivative of each factor with the prime in it, right? So t plus 1 square. 100 t prime is 100. T plus 1 minus 100 t. T plus 1 prime is just 1, right? So, we can simplify. So we can distribute. We get 100t plus 100 minus 100t. You see, there's a good thing we can cancel it. This cancel, we only have 100 over t plus 1 square. So that's the velocity, right? So part B, at what time is the marble 80 meters from the starting point? Okay, so what is this guy? We want to find the time, right? What time? So we want to find the time such that the marble is 80 meters. Sometimes from the units, you know what it's about. So meters is about the displacement. And if you see meter per second, that's about the velocity. So you want to find the time t such that, what's meter? The S of t equals 80, right? So we have 100t over t plus 1 equals 80. How do you solve for t? Well, both sides multiply by t plus 1. We get 100t equals 80 times t plus 1. Don't forget your baby, because next, when we want to distribute, we have 80t plus 80. If you forget the parentheses, then you have this guy has just become 1 instead of 80. So be careful of that. Both sides subtract 80. We get 2 and both sides subtract 80t. Then we have 20t on the left equals 80. Well, t is both sides divided by 20. 80 divided by 20 is 4. Okay, so the marble is 80 meters from the starting point at t equals 4 seconds. Part C, at what time is the velocity 50 meters per second? So we want to find the t such that, v of t equals 50. Well, we can solve it. So v of t 100 over t plus 1 squared is 50. Okay. We can flip both sides. Then we can cross multiply. So 100 equals 50 times t plus 1 squared. Both sides divided by 50. Then you get 2. So you can then take the square roots of both sides. Square root 2, but when you take square roots, you get plus or minus. Yes, be careful with that. So t is plus or minus square root 2 minus 1. But can your t be negative number? No. So we only pick the positive one. So that is square root of 2 minus 1 second. So far, so good, everybody? So, yes, at t equals square root of 2 minus 1 second, the marble has velocity 50 meters per second. Okay? All right. Let's continue and look at example 6. The population of a culture of cells after t days is approximated by the function p of t equals 1600 over 1 plus 7 e to the minus 0.02t. What is the average growth rate during the first 10 days? Well, what is that? Well, average growth rate over the first 10 days. So p of 10 minus p of 0 over 10, right? What is p of 10? Well, we plug t equals 10 into our expression, right? So 1 plus 7 e to the minus 0.02 times 10 is just 0.2. What is p of 0? Well, it's if t is 0, e to the 0 is 1. 1600 over 1 plus 7, which is 8. Oh, so this is 200 over 10. Right, so we plot this in our calculator and let's see what do we get. Okay, so I hope everybody can pause here and try to plug this in your calculator, because this guy, when you plug it into the calculator, it's very easy to make mistake, especially if you forgot to put the parentheses in the correct place. Then you get a mistake. So I hope everybody can try to plug in your calculator right now, because I do have a previous semester that some students asked me during the exam how to type this in the calculator. I can't answer these questions during the exam, okay? So I hope everybody can figure that out now, okay? In the exam, I can only answer questions like if you don't understand what the questions mean, I can explain to you what the question means, but I'm not supposed to tell you what to do or whether what you're doing is right or wrong, okay? So I plug this in my calculator and my answer is approximately 3.77. So far, so good, everybody? Okay. And then part B, find the instantaneous growth rate function P prime of t. Well, P prime of t, well, we're gonna do the derivative, right? So this is a quotient, so we use quotient rule. Actually, do you see the numerator? It's not a function of t, okay? So actually, later in the next session, after we learn chain rule, this problem is better to use the chain rule rather than the quotient rule. But I'm gonna do the quotient rule, and then after the quotient rule, I'm gonna do a chain rule, even though we haven't learned chain rule. But I hope that after we learn the chain rule, you can go back and watch this example, and then you can get it, okay? So quotient rule. The bottom is the bottom square. And then we have the top guy prime times the bottom guy. And then minus the top guy times the bottom guy prime, right? And then we have the bottom guy square. Well, this guy, 1600 is a constant. Derivative of a constant is just 0. So all this thing is gone. So 0 minus 1600. Derivative of 1 is just 0. Derivative of 7. Okay, so 7 constant multiple stay there. And then remember father looks like the sun, but father has the mustache. This is the mustache. E to the negative 0.02t. Alright, so now you can see negative cancel, and so this guy cancel, and this 2 zeros and this 2 zero cancel. So 2 times 16, 32. 32 times 7 is 224. E to the negative 0.02t divided by 1 plus 7 e to the minus 0.02t squared. Okay, so this is the quotient rule. Well, how do we use chain rule to solve it? Okay, so chain rule is next session, but after you learn next session, you can come back and watch this video for this part. Okay, so in order to use chain rule, okay, first of all, you want to rewrite the function, okay? So we want to rewrite into the standard form. So this is like 1600 times 1 plus 7 e to the minus 0.02t to the negative 1. Well, when you use chain rule, you consider the inner function be u. Then p prime of t is, well, 16 u to the minus 1 is 1600 minus 1 u, which is this guy, to the negative 2 times u prime. So that's why we get negative 1600, 1 plus 7 e to the minus 0.02t to the negative 2, u prime, you see, 7 stay here, and then this guy is minus 0.02 times e to the minus 0.02t. Okay, so this is the chain rule, and you can see is the same thing as here. Okay, but this guy is in the denominator, so the exponent is positive, and right now I put this on the numerator, so the exponent is negative, but they are the same thing. Okay, so they're the same. So far, so good. And I really want to point it out because sometimes students make mistake. Where do they make the common mistake? The common mistake is they forgot about the derivative of 1600 is 0. So they will still keep the 1600 here with this term. So which is wrong. So be careful with that. Okay, so this is session 3.5. We learned about derivatives and the rate of change. Okay, so the applications of derivatives. So in session 3.10, we will learn more about rate of change. Okay? See you. Bye.